Differentiation by rule. Differentiation by rule of algebraic and trig functions. Standard derivatives. The following standard derivatives are given on page 25 of the formulae and tables. So here we have the function f of x, and here we have the derivative f prime x. So if we have a function x to the power of n, then to get the derivative, we bring the power, which is n in this case, down in front, and we reduce the power by 1. If the function is equal to cos x, then the derivative is minus sin x. If the function is equal to sin x, then the derivative is cos x. If the function is equal to tan x, then the derivative is sec squared x. So here we have page 25 of our formula book, and we can see highlighted in yellow the 4 derivatives that we just went through. Each of these standard derivatives can be verified by using first principles. There are a number of issues to be discussed about these standard derivatives. Number 1, the notation for differentiation can be written in a number of equivalent ways. For example, from the formulae and tables, we are told if f of x is equal to x to the power of n, then f prime x is equal to n x to the power of n minus 1. But we can also write if y is equal to x to the power of n, then dy dx is equal to nx to the power of n minus 1. So dy dx, differentiating y with respect to x. And even replacing y with x to the power of n. So we can have d bracket x to the power of n bracket over dx is equal to nx to the power of n minus 1. So these are 3 different ways that we can write the derivative. Number 2, the first standard derivative tells us that if we differentiate a power of x, we bring the index down in front, keep the base, and reduce the index by 1, i.e. d x to the power of n dx is equal to n x to the power of n minus 1. So we're bringing the power down in front, sticking it on in front of the x or multiplying it by whatever is in front of the x, and then we reduce that power by 1. Rules of differentiation. The rules of differentiation are used with the standard derivatives to greatly increase the number of functions that can be differentiated. The rules themselves can also be proved by making use of first principles, but we are not required to do so. Rule number 1. If c is a constant and u is a function of x, then d c times u dx is equal to c times du dx. So to differentiate a constant times a function of x, we can take the constant outside and multiply it by the derivative of the function of x. For example, d 5 sin x dx is equal to 5 d sin x dx, which is equal to 5 cos x, because the derivative of sin x is cos x. Example 2, differentiate with respect to x. So 7x to the power of 4. So we can use rule 1 again. So we bring the 7, which is the constant, in front. We differentiate the x, so x to the power of 4 gives us 4x to the power of 3. And then we multiply 7 by 4 is 28. So we get 28x cubed. Or using, bring the power down in front and reduce the power by 1. If y is equal to 7x to the power of 4, we bring the power down in front, the 4 comes in front. So it becomes 4 multiplied by 7x, and we reduce the power by 1. 4 minus 1 is 3. So we get 4 times 7, which is 28, x to the power of 3. In practice, we would not write down the middle lines. Instead, we would bring down the index and multiply it by whatever coefficient the power has. So basically, we don't need to do the middle steps. And eventually, you'll just be able to do this in your head. Example 2, differentiate with respect to x minus 9x. So the minus 9 comes down in front, and then we just have to differentiate x, and the derivative of x is 1. And minus 9 times 1 is minus 9. Or, using the rule, bring the power down in front, reduce the power by 1. y equals minus 9x to the power 1. So the derivative of y equals 1 multiplied by minus 9x to the power of 1 minus 1. So the 1 came down in front, and 1 multiplied by minus 9 is minus 9. And then we reduce the power by 1. 1 minus 1 is 0. And x to the power of 0 is 1, so we get minus 9 times 1, which is just minus 9. In practice, to differentiate a multiple of x, the outcome is just the multiple. So basically, in practice, if you want to differentiate an x on its own, so not squared or cubed or to the power of 4 and so on, all we do is we just get rid of the x. So minus 9x, we could have just got rid of the x and got minus 9. Number 3, differentiate with respect to x, 12. So 12 is the constant, so again we bring the constant out in front, and it's really 12 times 1. So the derivative of 1 is 0, because there is no x to go on to the 1, and 12 times 0 is 0. Or in short, if y is equal to 12, then the derivative of y is equal to 0. The derivative of any constant is equal to 0. Because we were asked to differentiate with respect to x, and there was no x, so we just get 0. In practice, when we differentiate a constant on its own, the outcome is 0. Rule 2. If u and v are functions of x, then du plus minus v dx is equal to du dx plus minus dv dx. To differentiate the sum or difference of two functions of x, differentiate them separately. Keep the plus or minus sign between the two parts. Rule 2 is often used in conjunction with Rule 1. For example, d dx 3x cubed plus 2 sine x is equal to d dx 3x to the power of 4 plus d dx 2 sine x. So the derivative of 3x to the power of 4 is 12x cubed, and the derivative of 2 sine x is 2 cos x. And this is our answer, we just leave the plus in between. Example 3. Find dy dx if 1. Y is equal to 2x squared minus 1 over x. So we should write 1 over x as x to the power minus 1 before differentiating. So y equals 2x squared minus 1 over x can be rewritten as 2x squared minus x to the power minus 1. So dy dx is going to be 4x, so the 2x squared will become 4x. So let's have a look at that over here. So if y is equal to 2x squared, then the derivative of y is 2 times 2x to the power 2 minus 1. So we bring the 2 down in front, and we reduce the power by 1. 2 times 2 is 4, 2 minus 1 is 1, and 4x to the power 1 is 4x. So next we bring down the minus, and next we want to differentiate x to the power of minus 1. So we bring the minus 1 down in front, and we reduce the power by 1. Minus 1 is minus 2. So let's do it out here, the longer method. So if y is equal to minus x to the power minus 1, we bring the power down in front. So we have minus 1 multiplied by minus x, and then we reduce the power by 1. Minus 1 minus 1. Minus 1 by minus x is plus x, and minus 1 is minus 2. And x to the power minus 2 is 1 over x squared. So we had 4 minus 1 x to the power minus 2 minus 1x is plus x to the power minus 2, and x to the power minus 2 is 1 over x squared. So you could have gone straight from this to this, but I just did it out the long method so that you can see where I'm getting the numbers from and how the powers have changed. But as time goes on and as you practice these a lot more, you won't need to do these steps, you'll be able to do them in your head. So find dy dx if y equals 3 cos x plus 2 tan x. So y is equal to 3 cos x plus 2 tan x. So dy dx is going to be 3 multiplied by minus sine x, because the derivative of cos x is minus sine x, plus 2 sec squared x, because the derivative of tan x is sec squared x. The only reason we had brackets here was because there's a minus and you're going to have to multiply in the minus. So 3 times minus sine x is minus 3 sine x, and we just bring down the plus 2 sec squared x. So here we have the derivative. Once a derivative has been found, we can then evaluate it at any value of x for which it is defined, i.e. we can use it to determine the instantaneous rate of change of the function or the slope of the tangent to the corresponding curve. It is important to remember to only substitute values of x after the derivative has been obtained. Example 4. A function is defined for all x values elements of the real number set by f of x maps to x cubed plus 2x squared minus 5x plus 1. We want to find the derivative, f prime x. We want to find the instantaneous rate of change of f when x is equal to 3. And we want to find the slope of the tangent to the curve of y equals f of x at the point where x is equal to minus 1. So part 1, find the derivative f prime x. So our function is f of x equals x cubed plus 2x squared minus 5x plus 1. So f prime x will be 3x to the power 3 minus 1. So what I did was I brought the 3 down in front, and I've reduced the power by 1. Plus 2 times 2x to the power 2 minus 1. So again, I brought that power down in front, so 2 times 2, and reduced the power by 1. Minus 5x to the power of 1 minus 1. So x is really x to the power 1. So if you're bringing 1 down in front, 1 multiplied by minus 5 will just give you minus 5. So you don't necessarily have to write it in. And 1 minus 1. And then the derivative of 1 is just 0 because there is no x value, so we can't differentiate it. So now we just have to tidy up. So we have 3x to the power 3 minus 1, which is 3x squared. 3 minus 1 is 2. We have 2 times 2x to the power 2 minus 1. 2 times 2 is 4. X to the power of 2 minus 1, which is 1. So 4x to the power 1, or just 4x. And then minus 5x to the power 1 minus 1. So we bring down the minus 5. 1 minus 1 is 0. So we have x to the power 0, which is just 1. And minus 5 multiplied by 1 is just minus 5. And then we forget about the 0. Part 2, find the instantaneous rate of change of f when x is equal to 3. So what we have to do is take our derivative, which we worked out in part 1, which was f prime x equals 3x squared plus 4x minus 5. The instantaneous rate of change of f at x is equal to 3 is f prime 3. So we swap each of those x's for 3 with brackets around it. So f prime 3 is 3 times 3 squared plus 4 times 3 minus 5, which is 34. So the instantaneous rate of change of the function at x is equal to 3 is 34. Part 3, find the slope of the tangent to the curve y equals f of x at the point where x is equal to minus 1. So again, we take our derivative we worked out in part 1, f prime x equals 3x squared plus 4x minus 5. The slope of the tangent to the curve y equals f of x at x is equal to minus 1 is f prime minus 1, i.e. the value of dy dx at x is equal to minus 1. Thus, the slope of the tangent is 3 times 1 minus 1 squared plus 4 times minus 1 minus 5, which is minus 6. So what we did was we swapped each of the x values in our derivative for minus 1 with brackets and multiplied. So the slope of the tangent to the curve y equals f of x at x equal to minus 1 is minus 6.